Scattered through the vast emptiness of space are regions where gravity becomes so intense that nothing, not even light, can escape. These are black holes. They are among the most extreme environments the universe has ever produced, and they have fascinated astronomers for over a century. For generations, physicists asked a few deceptively simple questions. What happens when a massive star runs out of fuel? What lies at the heart of our galaxy? And can gravity ever become strong enough to imprison light itself? The answers, when they finally arrived, reshaped modern physics. Over the next few minutes, we will follow the life of a black hole from its birth and the death of a star, through the strange physics that surrounds it, to the slow fade predicted by quantum theory. This is the science of black holes. A black hole is a region of space where gravity has overwhelmed every other force. Its boundary is called the event horizon. Cross it, and no path, no signal, no object can ever return to the outside universe. It is a one-way surface, set by gravity itself. Astronomers recognize several classes of black hole. Stellar mass black holes, between roughly 5 and 100 times the mass of our Sun, form when massive stars collapse. At the centers of galaxies sit supermassive black holes of millions to billions of solar masses. A third class, the intermediate mass black holes, remains rare and elusive. According to classical general relativity, all the matter inside a black hole is crushed into a point of infinite density at its center, called the singularity. But infinities in physics usually mean a theory has been pushed past its limit. A future theory of quantum gravity is expected to replace this picture with something we do not yet understand. A black hole begins with a star. Throughout its life, a star is a steady balance between the inward pull of gravity and the outward heat of nuclear fusion in its core. When the fuel runs out, that balance fails and gravity takes over. For the most massive stars, the end arrives quickly. The core collapses in a fraction of a second, and the outer layers are hurled into space in a supernova, briefly outshining an entire galaxy. If what remains is heavy enough, no force can halt its collapse, and a black hole is born. A black hole does not stop growing once it forms. Gas, dust, and sometimes whole stars stray close enough to be captured, spiraling inward in a glowing accretion disk. Over billions of years, this steady infall is how the supermassive black holes at the centers of galaxies reach their enormous sizes. Near a black hole, time itself runs differently. Einstein's general relativity tells us that gravity slows the flow of time. To an observer watching from a safe distance, a clock near a black hole would tick more slowly than their own. The closer the clock, the stronger the effect. Anyone falling toward a black hole would meet a dramatic fate. The pull of gravity on their feet would be so much stronger than on their head that their body would be stretched into a long, thin strand. Physicists call this process spaghettification, and nothing material could withstand it. A black hole bends space so severely that light itself follows the curve. Background stars appear to shift, smear, and sometimes form bright rings around the dark shadow. This effect, called gravitational lensing, lets astronomers study objects lying behind the black hole that would otherwise stay hidden. Few places in nature are as violent as an accretion disk. Matter falling inward heats to millions of degrees, glows in X-rays, and whips around the black hole at close to the speed of light. These disks are the main way we observe the otherwise invisible. In 1974, Stephen Hawking applied quantum mechanics to the region just outside a black hole's event horizon. His calculations suggested something remarkable. Black holes are not completely dark. They emit a faint glow of radiation, now known as Hawking radiation, and given enough time they should slowly fade. A common way to picture Hawking radiation uses the language of quantum fluctuations. In empty space, pairs of particles and antiparticles appear and vanish in an instant. Near the event horizon, the story goes, one can fall in while the other escapes outward. Physicists treat this picture as a useful heuristic, not the literal mechanism. Through this slow leak of radiation, a black hole loses mass and shrinks. For a black hole the mass of our Sun, full evaporation would take roughly 10 to the 67th years, vastly longer than the current age of the universe. The endpoint, in theory, is a final burst of particles. At the heart of most large galaxies, including our own Milky Way, sits a supermassive black hole. Sagittarius A star, the one at the center of our galaxy, contains about 4 million times the mass of the Sun. These giants shape how galaxies form, heat, and age over cosmic time. Because black holes emit no light of their own, astronomers study them indirectly. X-ray telescopes trace the hot gas in their accretion disks. Gravitational wave observatories listen for the ripples in spacetime set off when two of them merge. And the orbits of nearby stars can reveal an unseen massive companion. In 2015, the LIGO observatories detected gravitational waves from two black holes colliding more than 1 billion light-years away, a result announced the following year. In 2019, the Event Horizon Telescope captured the first image of a black hole shadow in the galaxy M87. In 2022, the same team imaged Sagittarius A star at the center of our galaxy. Black holes are far more than astronomical curiosities. They test the limits of our two most successful theories, general relativity and quantum mechanics, in the same place at the same time. Anything we learn about them pushes the boundary of what physics can describe. Major questions remain open. What really happens to matter that crosses the event horizon? Does information survive, or is it lost for good? And how will a working theory of quantum gravity one day replace the singularity? Honest answers for now are simply that we do not yet know. If you enjoyed this journey, please like and subscribe, and tell us in the comments what you would like us to explore next.